There we go.
Okay.
Okay. Today we're going to be learning about factorials, permutations, and combinations. I don't know if you guys heard of those before, but it's okay if you haven't because we're learning about them today. Oh yeah, first we've got to review the homework. Okay.
Wait, did anybody have any problems doing the homework? Okay, well, we can start. I'm actually going to be calling on some people to see how they did it, and we'll see if, like, you got it right, or, we're just going to see how you did it, and we're going to go over it together. So let's see. I don't know how to pronounce this, so I'm really sorry about this. Ayan, Ayan. I don't know how to pronounce your name. I'm really sorry about it. But would you like to?
Yeah, that's right.
Okay, it's Ayan, right? Okay, did you do your homework? Okay, that's good.
Huh?
You did your homework, right?
Yeah.
Okay, that's good. So can you tell us what you got from number one?
Number one, I got 1/8.
Okay, that's nice. So how did you get 1/8?
1/2 to the cube.
That's right. Okay, that's exactly right. So 1/8 is the correct answer. Nice job.
Yeah,
Okay,
and you do. Wait, let's just quickly if just in case anyone didn't get it. Ein said that you do 1/2 cubed to get the answer. And the reason for doing 1/2 cubed is because you flip the coin 3 times, and the probability that you get head just in one flip is 1/2. But since you did it 3 times, we have to multiply 1/2 times 1/2 times 1/2, and that gives us 1/8.
Okay. Sahil, what did you get for number two? Hello? Sahil Tendulkar, I think. So I know you're there since you put something in chat. Okay, it's fine if you don't want to answer. Advika, you do your homework?
Yeah, I did.
That's nice. That's good. So what did you get for number two?
For number two, I got 90.
That's the right answer. So good job on that as well. So this is just a simple case of complementary counting. Did we teach you guys complementary counting?
We didn't yet, but it's okay.
Okay, yeah, but it's okay. This is a simple enough problem. So, there's just 9 multiples of 11 that are less than 100. So that'd be 11.233, and then until 99, right? And we know that there are 99 positive integers less than 100. So that'd be 1 through 99. So we know that there are 9 multiples of 11 less than 100. And we know there are 99 total numbers. So there would just be 99 minus 9. And we would get 90. So it's pretty straightforward. Does anybody have any questions on number two? Hello? No questions? Then we can move on. So 90 is the right answer. Good job. Harsh, what'd you get for number three? Harsh? Hello? I don't want to answer. I don't my answer. Well, it's fine. You don't have to answer if you really don't want to. Shreyan.
Okay. So question number 3, right?
Yeah, it's question number 3.
So I got 800 for the answer.
Uh-huh. Can you walk us through how you got 800?
Yep.
Did you use casework to solve this problem?
No, I just used a fundamental counting principle.
Yeah, that's
okay. Well, you can still walk us through it. Walk us through it.
For question number 3, question number 4, I think requires casework. Okay, so there are, for the first digit, 4 and 8 are the only possible digits we can use, right? Because they're multiples of 4. So there are 2 possible digits. Then for the second and third digit, there are 10 possible digits. And for the final digit, there are 4 possible digits, right?
Okay,
Because
so
2, 4,
that's where you might be a little wrong, and you were so close on this problem. So we have to include 0, right? Because 0 is actually a multiple of 2. So it's actually 5 possible digits.
You were very, very close.
You're very close. That's exactly the correct methodology. That's exactly what you should have done, but you excluded 0.
How is 0 a multiple of 2?
2 times
It's
0
less
is
than
0.
2.
Yeah,
But
it
2
is less
times
than
0 is
2,
0,
but
right?
Okay.
But look, think about it, right? 2 times 1 is 2. So anything that is multiplied by 2 is a multiple of 2, right? As long as it's like, we're talking about positive integers. I mean, not positive integers, just integers after all. And 2 times 0 is 0. So 0 is a multiple of 2. You guys understand that? 0 is a multiple of 2. Yeah. So there are actually 5 possible numbers that could be in the last digit. So it would be 1,000 instead of 800. So
yeah,
Harsh, did I call him Harsh or who did I call him? Was it
I think.
Shreyan?
Yeah.
Oh, I think I called him Shreyan, but yeah, you were really close. So
yeah.
good job.
Okay. Anyways, then you have to do 10 times 2 times 10 times 10 times 5. So the answer is 10,000.
Yeah.
Oh,
That's,
well, not
well, 1,000,
it's
but yeah.
1,000. You were close. Yeah, close enough. It's fine. Okay, you can. Okay, so we're done with number 3. Does anybody have any questions for number 3?
Wait, did I accidentally say 10,000? I meant 1,000.
Yeah, it's fine. It's fine. So, yeah, fundamental counting principle would be used there. A little bit of casework if you want to. You have a question for number 4. Well, we can get to number 4. So we're just gonna get to number 4 really soon. So I hope we can answer your question then. But yeah, we can do number 4 now. I'm gonna call on somebody else. Audit. Do your homework. No, it's fine. Oh wait. Audit. Hello, audit. All right, if you don't want to answer, it's fine. Okay, it seems like a lot of people don't understand number 4. Did anybody do number 4? Can I do it? Yes, Vishwa, do number 4 for everyone.
So my answer was 90 rectangles.
Mhm.
So I counted the single rectangles, the 1 by 2, the 1 by 3, the 1 by 4s, and then the 1 by 5s. And then I just reversed that, so just 1 by 2, 2 by 1, and then 3 by 1.
Okay, yeah.
And then after that, I counted the squares, so 2 by 2, and then 3 by 3.
Uh-huh.
And then I started counting the rectangles, so 2 by 3, and then 2 by 4 since 2 by 4, and then 2 by 5.
Okay.
And then after that, I counted 3 by 2, 3 by 4 since 3 by 3 is a square, and then 3 by 5.
Yeah. So looks like you did everything correct. Wait, what was your final answer?
90.
Amy?
Wait a second. Isn't this the same one we did in class?
Yeah,
or is it different?
yeah, that's what I was thinking. I was like,
Okay,
whoa, this
that's
problem looks
weird.
really. Wait,
I
what
don't
did we
think-
get for that problem? Wait, I think we got 90 for that. No, did we get
I
60?
believe it was 60 we got.
Yeah, I think we got 60. Here, we can wait, okay.
I'm currently drawing these out.
Okay. Wait, Amy, the diagram isn't completely visible. You might want to minimize that, or you might want to move to another slide.
Oh, yeah, okay. Here. There.
Oh, there is an extra column in this problem, apparently.
There's an extra column. Okay.
Well, we can still work
Oh,
through
okay.
it.
Yeah,
Yeah, we'll work through it
that
though.
will be a lot of rectangles though.
Okay, so look, there are 15 single squares, right? Wait,
Yeah,
have we
15 single,
have
12.
we accounted? Let me just check if we've accounted for all the yes, we have 2 by 3s. We've done 3x3s. We can do 2x4s and we can do 2x5s. Then we can do 3x4s and then 3x5s.
Yeah, I'm a little bit running out of room a little bit, but that's right.
And then we can do 2x3s. Well, Amy, maybe you don't want to draw them all out.
Yeah. Okay, that's all right. Like,
It's
okay, we
okay.
can write them out from now on. Okay, for the
Oh
one,
wait, it
for
looks
the-
like some people don't get it. Here, wait. I have a decent idea. So let me go to that Jamboard app. Let me try to. I'm gonna try my best to explain this. Okay.
You forgot
Actually,
the-
Amy, can you
actually,
copy
maybe
and
we
paste-
should hold on, Sai. Maybe we should come back to this after we finish the lesson for today, because
Okay,
in this
yeah, that's a
problem,
good
there's so
idea.
many rectangles that it's not very
Yeah.
efficient to even use casework. There's actually
Yeah.
another strategy you can use, but it involves today's lesson, which is about
Yes,
combinations.
actually.
So
yeah,
we can actually come back to this question.
Mhm. Wait, yeah. So number 5, is FCP. So I actually think Tanisha wanted to do this problem.
Sure. I got 144 since you would have to multiply 6, 8, and 3 together.
Yeah, that's right. So yeah, so 144 is actually the correct answer. So good job. Good job on that. So yeah.
Okay. So we're done with
Mhm.
the homework review now?
The homework, yeah.
Okay. All right, let's get into our lesson. So first topic of today is on factorials. So first of all, I want you guys to look at this question and write down or just put in the chat on mute anything that you notice about it. Like, is there something confusing? Is there something that you haven't seen before? And if you do know what it is, I mean, I guess you could write out what it is. Yeah.
Yes, so it looks like some of you guys already know what it's called. It's called a factorial.
Yep. Yeah, that exclamation point is a factorial. So it looks like a lot of you also already know what a factorial is, which is good. So the factorial of a number is equal to the product of all the positive integers that are less than or equal to that number. So, for example, as some people have put in the chat, 5 factorial, which is 5 followed by an exclamation point, would be 5 times 4 times 3 times 2 times 1. That would be equal to 120. And as another example, 4 factorial, which is 4 followed by an exclamation point, is 4 times 3 times 2 times 1, which is equal to 24. And of course, you can basically do this with whatever number as long as it's a positive whole number. And yeah, so for example, 10 factorial, you multiply out all the numbers from 10 to 1, and you get 3,628,800. And here's another thing. What is 0 factorial? 0 factorial is actually equal to 1. I don't exactly remember why. It's been a while, but okay. However, just do remember that 0 factorial is not 0. It's actually equal to 1. I don't remember the proof for it though, so sorry.
Wait, I think I might know. Okay, so it's just something that I've been like I've been kind of like, okay, so here, I'm just gonna it's gonna be very simple. So here in the chat, I'm just gonna put something. So 5 factorial is 120, right? 4 factorial is 24. And this is not exactly a proof. 2 factorial is 6 and 2 factorial is 2, right? So what you're gonna notice is that obviously we're dividing by the number below. So 120 divided by 5 is 24. 24 divided by 4 is 6, and then 6 divided by 3 is 2. So if the pattern were to continue, wait, I think I messed something up. Wait, if the pattern were to continue, then wait.
Oh yeah, you're right.
is-
If the power were
yeah.
to continue, you have 1 factorial equals 1. And to get
One.
from there, you divide 2 factorial by 2 to get the
Yeah.
1 factorial. However, this means that in order to get 0 factorial, you have to divide 1 factorial by 1, which is just 1. So even though it's kind of weird, 0 factorial is actually equal to 1.
Yeah, that's the pattern. It's just a pattern. It's
Yeah.
based on the pattern. That's why it's 0. It might be a little confusing to some of you, and honestly, it kind of is kind of a little confusing, but like it's a pattern, so that's how that's done.
All right. So now we can look at some problems or like equations that involve factorials. So you guys can unmute or answer in the chat. Evaluate 3 factorial. Yeah. Yeah, it looks like you guys got it. The answer is 6. This is because 3 factorial is equal to 3 times 2 times 1. That's just equal to 6. It's pretty easy. Now evaluate 6 factorial. Yeah, nice. It looks like you guys also got that too. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is equal to 720. Now let's evaluate 6 times 5 factorial. Yeah, this would also be equal to 720. And if you expand this, this would actually be the same thing as 6 factorial. Because 6 times 5 factorial is just 6 factorial. So that would just be 720. Basically, what we've done is we've just pulled out the 6 and just left all the 5 factorial within it. So here's something that you should probably notice about factorials. So if we have something like, let's just, you guys can't really see that. Okay, if you have something like 6 factorial where it's like 6 times 5 times 4 times 3, 2, and 1, you have to notice that it has a bunch of factorials inside of it. So 6 factorial has a 5 factorial inside it. Also, it has a 4 factorial inside it. And it also has a 3 factorial and a 2 factorial and a 1 factorial all inside of it. And this is really helpful when solving more complicated problems, because then it means you don't actually need to multiply it out. You can just pull out the numbers you need. So you can do this slide.
So, oh my bad. All right, so you guys can just evaluate 3 factorial plus 4 factorial. Okay.
Oh, we have a question about the previous question.
Wait, what last question? This
6 times 5.
All
This
right.
one?
So
Yeah.
Okay, so think about it like this. You know what a factorial is, right? Factorial is just 5 times 4 times 3 times 2 times 1, right? Because that's 5 factorial. Because we're just multiplying everything down to 1 from that number. So do you understand that?
Yeah.
So when we're multiplying 5 factorial by 6, you notice that we're actually multiplying 6 included in that. So 6 times 5 times 4 times 3 times 2 times 1. So 5 factorial times 6 is actually 6 factorial.
Oh.
Yeah, because we're also multiplying by 6 now. So now that 5 factorial multiplied by 6 becomes 6 factorial, and 6 factorial is just 120.
Okay.
Yeah.
Thank you.
Okay.
So yeah, as I said before, everybody can just evaluate this 30. Yep, so the answer is 30. That's good job with that, guys. So there's actually, like once you get into more complicated problems, like bigger factorial numbers, there are easier ways to do this. Wait,
this
why?
is addition.
Yeah, it's just addition.
Yeah.
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 So I wanted to just show you guys something, right? So if it was 6 factorial plus 7 factorial, I'm just gonna put that in the chat.
Something that you could do is you guys know what the distributive property is,
Yeah,
right?
so what you would do is just do this, right? So does everybody know the distributive property before I continue? Okay, yes, I just wanted to make sure. So this is what we would get when we factor that. Does everybody understand why? Because when we expand it, we get 7, which basically equals 6 factorial plus 7. So when we expand that, we get the same thing. So then it's basically just 6 factorial times 8. So by factoring, it becomes a much easier problem, which is 720 times 8, which is what, 5760, if I'm not wrong.
Yeah, I think
That's
so.
the answer.
Yeah, so that's
So-
easier than multiplying out 6 times 5 times 4 times 3 times 2 times 1 plus 7 times 6 times 5 times 4 times 3 times 2 times 1. Like
That's
if
just the
instead you just take out the 6 factorial, you factor it out using the distributive property, then it turns into 8 times 6 factorial. And if you actually memorize your factorials, then this actually becomes pretty easy because you already know what 6 factorial is. So,
Yeah.
Yeah.
It becomes pretty easy. So we can move on.
okay. All right. Now let's look at another expression. Evaluate 4 factorial divided by 3 factorial.
Yeah, so it looks like you guys are immediately getting the right answer. So this problem is pretty easy, right? Because all we're doing here is just taking 4 factorial and dividing by 3 factorial. So we know that the 3 factorial can cross out with everything until the 4, right? So we would just get 4. So if we expanded that out, it would look something like 4 times 3 times 2 times 1 divided by 3 times 2 times 1. So we cross out the 3 times 2 times 1 on the denominator and the numerator side, and we just get 4. So it's a really simple problem.
Yeah, but it's
So this
even though technically you could just multiply out 4 times 3 times 2 times
Wouldn't
1,
be
which is
efficient.
24, divided by
It wouldn't-
6. For larger problems, like you don't want to be multiplying out all the individual numbers, which is why these properties are really useful.
So does anybody have any questions as of now, or does anybody have any questions yet? Anybody, any questions? If there are no questions, then we can just continue.
Okay, I guess we'll continue. Same thing that I just showed. All right, so back to the problem which we were initially shown. Evaluate 5 factorial plus 4 factorial divided by 3 factorial.
And please don't like actually do this, like don't calculate this by like, expanding each factorial. There's a much easier way to do this problem.
Yeah,
So that's, you should
do it using the
probably
properties, the distributive property.
Yeah. So Vishwa, you're right. It is 24. Can you explain to us how you got 24? Vishwa. I did it out. Okay.
Oh,
Well,
yikes.
that's not the best way to do it. Let me explain. So in the numerator, we're gonna first factor out 4 factorial. So we would get something like 4 factorial times 1 plus 5. 5 plus 1. Yeah, either way makes sense. Then we would divide that by 3 factorial. So we just learned that, well, not learned. We just figured out the 4 factorial divided by 3 factorial is simply 4 because the 3 factorial cancels out. So we get 4 times 5 plus 1. That's just 4 times 6, which is 24. So it becomes pretty simple.
Yeah.
So see how we just simplified that? We didn't even need to expand anything out. It's a very efficient way of solving this problem. You don't need any expansion of any sort, and it just becomes easier to solve. Does anybody have any questions on how I did that?
Oh, okay, I
Yeah,
can
okay.
show you. So basically, okay, let me go back a little bit. So when you have 5 factorial and 4 factorial, remember that 5 factorial, we can rewrite it as 5 times 4 factorial because, it contains the 4 factorial inside of itself, but it has like that 5. And so when we write it out, this is the same equivalent expression. It's just we pulled the 5 out of the 5 factorial. So we get 5 times 4 factorial plus 4 factorial, and then all of that divided by 3. Now we can use the distributive property to basically pull this 4 factorial to the outside of the parentheses. So this becomes 4 factorial times 5 plus 1 over 3. And the reason, where did this 1 come from? There's an invisible 1 right here because I just didn't write it out. Like, so when you pull it out, there's just a 1 there to okay, this is kind of hard to explain. when you can multiply this back into itself, and you can see that when you redistribute these two numbers together, you get 5 factorial. And when you redistribute these two numbers together, you get 4 factorial. So this is the same expression. We just pulled the 4 factorial outside of the parentheses. I hope that made sense. Yay. Okay, that's great. Yeah, so then from there you can, oh shoot, I forgot that.
Maybe add the factorials.
Yeah. Yeah, and from there you can just do the same canceling thing we did. For the 4 factorial and the 3 factorial cancel out to 4. That's just 4 times 6, which is 24.
Why do you cancel out the 4 and the 3?
Hold on, let me go back. Okay, so remember that this is 3 factorial, and the 4 factorial will actually have, will be 4 times 3 factorial. So let me replace that there, if I can find the eraser. Okay, this would actually be 4. Okay, 4 times 3 factorial times this expression. So then you can cancel out this 3 factorial, and you're left with just the 4.
Oh. Okay.
Yeah.
I thought you crossed out the 4 and 3, so I got a bit confused.
Oh yeah, I didn't mean to do that, sorry. Okay, any other questions?
Okay, so if there are no other questions, I think we're going to be moving on to our Jamboard.
Yeah. Okay, I'm gonna put the Jamboard link in the chat. Just this Jamboard is gonna be used throughout the lesson. I'm gonna ask you guys not to try to move ahead and do all the next questions. Just try to
Don't do that.
Yeah, don't be trying to move ahead, because yeah. I mean, I
Yeah,
know
because
some of you
remember-
guys will probably want to, but yeah.
So,
We're
just gonna
on
ask if we
slide
did
number
teach you
2.
Yeah, slide number 2, 2 problems. We're gonna go through this as a class, right? As a class. So I'm gonna call on some people to do this, and I want them to actually write. So when I call on you, please write. Feel free to write on the Jamboard and take us through the process of solving this problem. And please use the distribution method, something that we've told you, so we can actually see you guys apply these concepts. Don't bash it out. Don't bash out these numbers. Let's see. Charvi, do you want to do the first problem? And also, can you guys stop drawing with the laser?
Sorry.
It's fine. Oh, no, it's fine. Yeah. There's a lot of lasers. There's a lot of lasers. So Charvi, do you want to do this problem right here? One that I underlined.
Yeah, sure.
Okay. So you can just write on it. Just write on the Jamboard. Just take us through your just take us through your process.
Yeah, so first I'm going to do 6 factorial
Mhm.
times 7 plus 1
Right, that's nice.
divided by 8. And then I'm just going to cancel out these two.
Wait, 8 or 8 factorial?
Oh, oops, 8 factorial. So and so I'm going to cancel out the 6 factorial. And then I'm left with 8 times 7.
Mm-hmm.
So then I get 8 divided by 8 times 7.
Right.
And then I can just cancel out the 8. And then I
Right.
get 1 by 7.
Okay, that's perfect.
Yeah,
That
that's
is
amazing. That's
actually
great.
perfect. You did everything exactly right. And another way you could have done it is cancel out, the 7 and 1. So you could have just made that an 8, and then you could have canceled out the 8 and 8 factorial, right? Because 8 divided by 8 factorial is what? It's 1 over 7 factorial, right? We could have had a 7 factorial in the denominator, so it would have been 6 factorial over 7 factorial, which is 1 over 7. But your way is perfect. You did everything exactly right. So great job. Let's see. Yeah, excellent. Now we're gonna move on to the second problem.
I
So
think
yeah,
someone in the chat volunteered to answer it.
let's see who volunteered. Advika, do you want to do the second problem?
Yeah.
All right, then you can go for it. Oh, I thought that was the laser. I'm just gonna.
Okay. So first, I would apply the distributive property. So we have 3 factorial. And then in the parentheses, we have 1 plus 4. And then plus, I did 20 since it'd be 4 times.
Yeah, that's exactly. You're right. You're right because it'd be 4 times 5, which is 20. So that's right. You're right.
And all that divided by 6 factorial. Now I want to cancel out first, so it would be 25, and then on the bottom it'd be divided by 6 times 5 times 4.
Bishop will go over that later.
And then next we just cancel it out. So this would be 1. This would be 5. And I think the answer is 5/24.
That's right. Wow, that was brilliant. You guys are really doing so well with these problems. Yeah, that was good. Okay, you did everything exactly right. So that was a great job. So the 5/24 is the right answer. You did everything that you were supposed to do. You factored out the 3 factorial. You got this. You canceled everything out and you got the right answer. So great job.
I'm gonna answer some of the questions in the chat. So first question was,
Okay.
how did you get 20? The 20 came from the 5 factorial. When the 3 factorial was pulled out of the parentheses, that meant that the remaining part of the 5 factorial would just be 5 times 4, which is 20. The other question was, how did you get 25? The 25 comes from the parentheses. So the parentheses, what's left in the parentheses after you pull out the 3 factorial is 25. So 1 plus 4 plus 20.
So you guys did a great job. You guys all solved the problem correct. So the 2 of you who did solve the problem, you guys did it right. Does anybody have any questions?
So you know how you did 5 times 4 to get 20?
Yeah.
Why didn't you do 4 times 3 on the 4?
Okay, because, well, if you think about this, I'm going to show you. I'm just going to, is this my pen? Okay, cool. So think about this.
Oh, never mind. 4 times 3, 12.
Yeah. 4 factorial is just 4 times 3 times 2 times 1, right? When we have the 3 factorial, we're just only factoring out the 4 because 3, 2, 1 is in the 4, right? So we would only factor out the 4 there. But for 5, it's 5 times 4 times 3 times 2 times 1, right? So all of this, but 5 times 4. So we have to include 5 and 4 in the parentheses. So that'd be 5 times 4, which is 20. Now, if we were to do 6 factorial, what would we get? What would be in the parentheses? If I wanted to factor out, if I wanted to factor this out. If I wanted to factor out 3 factorial plus 6 factorial, what would I get in the parentheses?
3 times 1 plus 6 times 5 times 4.
6 times what's?
Yeah, 6 times 5 times 4. That's right.
Get this, exactly. So you guys seem to understand that. I'm going to erase my word. Well, there's no efficient way to erase this, but we can just move on.
I could just scribble all over it. Okay, I'm erasing most of it. All right, it's fine. Okay, back to the slides.
Back to the slides. Okay, you guys did a great job.
Yeah, that was, you guys killed it. Okay.
Should we keep the Jamboard open?
Yeah, you can keep it open because
you can
we'll be
just do it
coming
in
back to
another
it.
tab. Yeah,
Okay.
just keep open another tab.
Okay. All right, so now that you guys have pretty much understood the concept of factorials, we're now going to be moving on to permutations. And actually, you guys have already sort of started doing some permutations in our last class. It's just I didn't exactly call it by that name. So if we have this question, Michael wants to know how many ways he can arrange the letters in his name. So for example, Michael, that's one arrangement. MCIHEL is another arrangement, and all of these are also arrangements of the letters in his name. And basically, he wants to find how many ways you can arrange the letters in his name, but listing out every single arrangement is going to be time consuming. So we're going to be going over a strategy that he could use to, oh yeah, you guys are kind of like already getting it. So yeah.
Okay, wow.
Yeah, basically, I'm still going to go over it. We can use the fundamental counting principle to help solve this problem. Since there's 7 letters in Michael's name, there are basically 7 positions that the 7 letters could go in. And so here's my pen. Okay, so 1, 2, 3, 4, 5, 6, 7. We can basically think about it as like we're going to choose a letter to go in each blank. So for the first blank, we've got 7 letters to choose from because we have all 7 letters in his name available. And then for the second blank, though, we've already used up a letter in this blank. I don't know what this letter is. It doesn't matter. So we only have 6 letters to choose from. And yeah, and so we keep going. We have 5 letters for the third one, 4 letters for the fourth one, 3 letters, 2 letters, 1 letter. And by the fundamental counting principle, we multiply all of these out to get 5,040, which is exactly what a lot of you guys said in the chat, which is pretty great. Yeah, and basically, if you haven't noticed yet, this is 7 factorial, which is sort of why we introduced factorials first. So, yeah.
Before we continue on, Amy,
Yeah.
I wanted to clarify something, and I don't know if this is something we should talk about just yet, but if I duplicate letters, then
Oh, we're gonna get to that later.
all right, I just wanted to make sure because that's important as well.
Yeah, we're not going to talk about duplicate letters. Right now, we're just looking at names where each letter is different, such as this name.
That's
So,
good.
yeah, these problems, it looks like you guys already know how to solve these problems. You just take the factorial of the number of letters in the name that you're arranging. So, are there any questions?
If there are no questions, then we can just continue on with the next slide.
All right.
So,
Skipping over all that because I already explained. Okay. So yeah, this is basically what a permutation is. Oh yes, there is a formula, but we're going to introduce a formula for combinations, but I'm not sure it's necessary for permutations. So yeah. A permutation is the number of ways you can arrange a group of objects, such as the letters in someone's name, where the order of the objects being arranged matters. So, you guys, what are some other situations that we might need to count the number of permutations of?
How many times I'd have to buy the lottery to get a guaranteed win?
That actually
really
that might actually be expected value.
Yeah, that'd be expected value. Oh, that's not even expected value. It just depends on the jackpot, like how many jackpots there are. Expected value kind of calculates for like your weight. It doesn't really calculate for that necessarily. But that's in
Combinations of a lock, that's a good one.
good one, yes.
Yes.
It's like the total combinations you could have depending on the digits, the characters.
Yeah. I've got one. How about people going into a movie theater? Like maybe you're going to a movie theater with your friends and you need to figure out which arrangement you guys should be sitting in what order you can put the books in. Yes, that's right. Yes, we do use permutations for dependent probability. So yeah. Yeah, basically those are different situations which you might need to count the number of permutations in. just remember that in a permutation, it is the order of the objects that you're arranging matters. And yeah, that's like the biggest thing. So yeah.
And it's different in combinations, and there are formulas for both of them, but you probably wouldn't need the permutation formula. Like I think the combination formula is a little more important.
Yeah. Okay, now we're gonna
Okay,
do
so we
some
go on to the Jamboard, and
problems.
please go to slide 4 on the Jamboard.
Yeah.
Slide 4. So this slide right here. We're gonna be doing the problem together. So I'm gonna be calling on someone who has a good idea. Well, who wants to solve this problem for us? We get any volunteers? Can I try? Yeah, sure. Sahil, you can try to do this problem. Go to slide 4 and just walk us through your process.
Would it be 5 factorial?
Read the question
So we have
carefully.
to read the problem carefully. So it says such that the number 5 is always in the leftmost position. So what would be the leftmost position? It would be this one, right? So number 5 will always be here. So think about this.
Yeah. Right there. Oh, so 4 factorial.
Exactly. So if number 5 is always on here, then there are 4 other slots, right? And there are 4 ways we can arrange. There are 4 friends, right? Or not friends, sorry. 4 cards. So we can just arrange that in 4 factorial or 24. Good job, because 4 cards can go here, 3 cards can go here, 2 cards can go here, 1 there, multiply everything out, 24. That's the right answer. You guys seem to understand that. Does anybody have any questions? Probably shouldn't have erased everything. No, okay, that's great. So it looks like we got this problem right. We can move on.
Okay, this next problem. You need to schedule 5 classes for the day: algebra, history, English, biology, and physics. However, you don't want to have biology, physics, or algebra directly after each other. And so how many ways would you be able to schedule your classes then? And as an example, if in case you're confused, you can't have this arrangement: algebra, physics, history, biology, English, because algebra and physics are directly after each other, and you don't want that. So, yeah. So would anyone like to attempt this question, or does anyone have any thoughts of what to do first?
Yeah, Charby, you can
Yeah.
try.
Okay, so first we have 5. Wait, do I write on the Jamboard?
Yeah,
Yeah,
sure.
go ahead.
So we have 5 different ways to have like choose the first class. And then we only have 3 different ways because the other 2 classes will because biology and physics can't be directly after algebra if this is algebra, so there's only like 3 ways to choose the next class. And then afterwards we have 4 ways because these 3 aren't going to be biology, physics, or algebra. And then we have 2 ways to choose, and then we have 3 ways to choose the next class.
So
I mean, that's a creative approach. However,
it is a
I
creative
want
approach.
to ask something about this. So you're saying basically we can basically choose anything for the first class, right?
Yeah.
Okay. So, but then after that, you only have 3 choices. So why would you only have 3 choices next?
Because in those 5 different classes, one of them could have been algebra, so you can't have biology or physics as the next class, which means you would only have.
But
Wait,
what if you don't have algebra first? What if you have like some other class like history or something? Then you could basically choose any class, right?
Yeah.
One more thing.
Wait, I
You
don't
can't.
get it.
Okay, this problem is going to be a little tougher than your average problem. Yeah, yeah, yeah. Amy, I think this problem is definitely way too hard.
It's not that hard.
Oh,
It's not
I
that
think.
hard
Well, I don't
actually.
think.
I can give you guys a hint. I hope you don't mind. I'm going to erase your numbers.
Okay,
Okay,
Shreyan.
think about
Actually,
it like
Shreyan said he
this.
thinks he knows how to solve it. So, okay, that's
Think
good.
about it like this. These three classes, biology, physics, and algebra, you don't want them directly after each other. So let's just look at these three classes first, because these three classes have this weird, they have a restriction basically. So where could these three classes go in your schedule?
They would have to be like first, third, and fifth.
Yeah,
Exactly.
exactly. You can't put them anywhere else, because if you put like one of these classes here, then your other two classes have nowhere to go because they can't go here and they can't go
They would have to be
here. They would have to
consecutive. Yes.
they would have to go here, but that would mean they're right next to each other, and you don't want
They
that.
would have to
So
be consecutive. So these three classes have to be in the first, third, and fifth slots. Right?
yeah, they would have to go in first, third, and fifth.
Wait, does
Does
everybody understand that? Like,
oh
do you
yeah,
guys understand why that arrangement has to be first and fifth? Okay, good. Yeah, I thought that might be a little hard for some people to understand, but yeah, it's definitely a pretty easy problem, but I just wanted to make sure everybody understand this. So yeah, it would have to be first, third, and fifth, right? So I think somebody can solve it from here, right? Because how many other classes do we have? Oh, okay. Wait. So before we even get to that, I shouldn't have even done that. Sorry. So we have biology, physics, and algebra, and they have to be in the first, third, and fifth slots, right? So how many ways can we arrange that? How many?
6.
Advika, Advika, do you want to solve that? Or
Yeah.
okay, go ahead.
Okay. So for the first class, since we only have three choices, biology, physics, or algebra. For the first class, there are three choices. And then in the second class, there'd be two choices, which would be the history and English classes.
Right.
And then after that, there'd also be two choices here because if I were to like pick biology for this, there'd be physics and algebra left.
Mhm.
So then in between this, so if I pick history for the second class, now
Yep.
there'd be English, and then after that, there would be like algebra. So
That's
one.
exactly it. And there's only one choice at the end, right? So that's 3 times 2 times 2 times 1 times 1, which is 12. That's exactly it. So like that was a really good job. So yeah, 3 slots. This is how I would. It's kind of the exact same thing. So if there's 3 slots, there are 3 factorial ways or 6 ways I can arrange those 3 classes in that specific order, 1 through 5. And then there are only 2 other classes left. So let's just multiply that by 2 and we get 12. So yeah, this problem is pretty straightforward. And
you just have
it
to
wasn't.
think
It
about it
wasn't.
a little bit at
Yeah,
first.
so yeah, you have to think about it. You have to think about this just a little bit. But once you like understand that there are 3 slots, like that there's only a certain way we can arrange these classes, then it becomes pretty easy.
Yeah. So are there any questions about this? No questions? Okay. All right, we're going to be moving on to another problem. Slide 6. Okay, now it's for a locker combination, or as they should be called, permutations. Lily's
Because
locker
order matters.
because order matters. So Lily's locker combination. Oh, I see we have a question about the previous problem.
Let me see.
Okay. Someone is saying she does not understand why there is a 2 twice. Okay, maybe we could think about it this way. You see these ones that are like circled? These two go together. These 3 go together. These represent the classes where you can't have them next to each other. So this would be 3 times 2 times 1. However, these right here represent represent English and history. Basically, you could think of them as like being arranged independent of each other. If I like move, I can't move it. Oh shit. Okay. So for like biology, the arrangement of the biology, physics, and algebra is the 3 times 2 times 1. But then the arrangement of the history and English is 2 times 1. So if you write out the actual amount, it would be 3 factorial times 2 factorial, where the 3 factorial is referring to the arrangements of biology, physics, or algebra, and the 2 factorial is referring to the arrangement of history or English. The reason why there's a 2 twice here is because they're sort of like intermixed with each other, but really it's just 3 factorial times 2 factorial.
Exactly.
Okay.
So try to consider these permutations independently. So this 1, 3, 5 would be considered differently than this 2 and 1. So first we consider how many ways we can arrange the 1, 3, 5. So the plus 1, 3, and 5, because we know that order has to be for biology, physics, or algebra. And there are just 3 factorial ways we can arrange that. And then for the second and fifth slots, there's only 2 classes left over. There's only 2 ways we could arrange those 2 classes, right? We just interchange them. So just be 3 factorial times 2. It's just that.
Okay. No other questions? Okay. All right. Lily's locker combination, again, should be a locker permutation, consists of a letter, a number, or by a number, I mean a digit. A digit, okay. Okay, let me change that. A letter followed by a digit followed by a digit. How many possible combinations does her locker have?
I'm gonna call on someone for this. Let's call on someone who hasn't really gone yet. So like Suvidi.
Yeah.
Yeah, do you want to solve this problem for us?
Sure. So the letter, wait, this is letter in 2 digits, right?
Yeah, so a letter and 2 digits.
Okay, so her locker can have 26, 10, and 10, because there are 26 letters in the alphabet and 10 numbers.
Yeah, there are 26 possible ways we can get the number letters, so I'm just gonna write that.
Yeah.
And then how many ways can we get a number? A digit?
10.
10. And how many ways can we get another digit?
10.
Yeah, they don't have to be different. So that's another thing. So then what would our answer be?
Yeah, so it would equal 2,600.
Yeah. Yeah, this problem's a little bit easier.
This is an easy problem.
Yeah.
Yeah, good job. Nonetheless, good job.
Mhm. All right. Okay,
Oh,
next.
what is
Sure.
this?
Oh, what?
Looks like we have a very nice drawing on slide number 7.
Oh. Wow. Okay. All right. Well, I'm gonna have to erase that. I guess you could like draw it afterwards because we're gonna need a little bit of
It's
room
okay.
on this slide.
It's a good drawing.
Okay.
Okay.
All right. Could
uh,
I can do this problem if you don't mind.
Okay.
All right. So this problem: Alex, Bailey, Clover, Derek, and Edward go into a movie theater and find 5 seats, consecutive seats. Derek and Bailey want to sit next to each other. Edward and Clover want to sit next to each other, and Alex doesn't care where he sits. And how many ways can the 5 friends sit in the movie theater? So
The way this problem is done is actually pretty interesting, by the way.
yeah.
Pretty interesting. Shreyan, I think I know how you got 6, and you're actually so close. You're just missing one tiny thing. No, okay. So I think does anybody know how to solve this problem? Like
Or does anyone just have any thoughts on how they would
any
approach
thoughts?
it?
Yes. Yeah, Shreyan, you're actually really close. Oh, actually, Shreyan, you want
Oh,
to tell us how you got 6? Wait, just give me a second. What, you want to tell us how you got 6? Okay,
Yeah, I
so just
realized I
go ahead.
made a mistake though. The thing is that I just assumed them what Edward. So if we just say that all of them are just combined, we could just say Alex, right? We as one, and Bailey and Derek and Bailey want to sit next to each other. I considered them as one, but then after I was done solving the question, I realized Bailey and Derek could switch spots and still be the same.
Exactly,
So that's what
exactly.
happened.
Nice job, nice job, nice job catching that.
So
So,
should the answer should make Mike be I
so what would you get your answer? So after realizing that Bailey and Derek could interchange and that Clover and Edward could interchange, what would your new answer be?
oh wait, so there are two ways B and D could sit and there are two ways C and E could sit. So I think it's just
You're almost there. Come on.
there should be why am I not able to think right now? I mean if there's 6 ways,
Mm-hmm.
I mean I don't know will it be 12 because then oh no
Okay,
no it shouldn't be.
you're actually almost there. And I'm just gonna
I think
help you just a little bit. Okay, you're
20
so close.
24 then.
Yeah, 24. That's the right answer. So you got the right answer, 24. Good job. But I'm just gonna explain this for some people who don't understand. So we know that Derek and Billy want to sit next to each other, and we know Edward and Clover will also want to sit next to each other, right? So they want to sit next to each other. So we know that they're like they can't be separated, right? So we can just consider them one person now. So Alex is
or
his
at least
own
not
person.
maybe one person, maybe just
Yeah,
one
okay, yeah, not one
container.
person, but one group, yeah,
Yeah,
a
a group
container.
or
Okay.
container.
Yeah. Okay. So at this point, instead of five, trying to arrange 5 people, we can just consider this problem as arranging 3.
Yeah,
So
it
this
would
is a
be
container, this is a container, and
yeah.
this is his own person. So 3. So then that would just give us 6 total ways. But wait, we're not done yet. We have to realize you guys can switch seats. So they would still be sitting next to each other, right? So pretend that in their little container, they can still switch seats within their little container. So if there are 2 ways they can switch seats here and 2 ways they can switch seats here, then that gives a total of 24 since we multiply 2 and 2. So I have 6 total combinations. If Derek and Bailey switch seats, then that gives us an extra 2 because Derek and Bailey can switch seats, right? So that gives us 2 more permutations, and then E and C, Edward and Clover switching seats would give us another 2. So since they can switch seats, that would give us 2 times 2 more. So 4 times more permutations, so that would give us 24. Does everybody understand?
How come you can't like put Alex in the middle?
You can.
We can put Alex in the middle. So go for that.
Just let me scoot everything.
Okay, so some you guys are still a little confused. So I'm actually gonna try to explain this a little more in depth. Give me a second. I'm just gonna erase it. Yeah, looks like a lot of people are confused.
Basically, what we're saying is that since we know that Derek and Bailey want to sit next to each other, we could think of them as like going together through the movie theater, I guess. And then same thing goes for Edward and Clover, since they want to sit together. So on the screen, I don't know if you can see it. We've got these big rectangles, and I'm putting them around
You can see it.
Derek and Bailey and Edward and Clover. And basically, I'm grouping them together because we know that these 2 people have to stay together. So once you group them together, we can just, for now, let's just ignore the fact there's actually 2 people in here and just consider it as like one person. So now instead of having 5 seats, we basically have 3 large seats. So we can like shift these people around. We can put Alex in the middle if we want. We can move the Edward and Clover container over there. Or I'm just gonna leave it here because it's gonna be a pain to move it around. Basically, we can arrange these 3 people on this one, and this one in any arrangement. So how many arrangements would we have of these 3 people? of sorts?
6.
Yeah, we would have 6 because it's 3 factorial. So once we have that arrangement of 3 people, we have to now look inside these containers, because remember that there are other, like, multiple people in these containers. So for example, Derek and Bailey are sitting in one container. However, they could switch spots in that container, but it would actually be a different arrangement, but we didn't take this into consideration when we were just looking at the 3 containers, 3 people. So this means we have to multiply by 2 because Derek and Bailey could switch spots in their little container. And we also have to multiply 2 by a second time because Edward and Clover could switch spots in their little container also. What if B, D, E, and C sit together, but they are both side by side? Would that change anything? We could do, I hope this is what you're asking about, if this happens.
Yeah, because they're still in
Yeah,
the same container. Look, because D and B are still in the same container, E and C are still in the same container, so it's just a different arrangement. It still satisfies all the conditions. You understand that?
Yes.
Because all we need to do to satisfy that is just make, as long as D and B and E and C are sitting next together, any arrangement of switching seats within their container would make sense. And remember, the container is just figurative. It's just a way of thinking about this problem that makes it a little easier.
I
There's
have
not
another
an actual.
I have
Yeah.
another question. In one position, there's 8, and then there are 3 of the positions. So we multiply by 3.
Okay, so here.
I think I know what you're coming at. In one position, there would actually, if we just, I assume by positions you're talking about the 3 containers, if you will. So if you have the 3 containers, you would have 4 because C and E could swap. So that would give us 2. And then D and B could swap, which gives us 2 arrangements in there. But then you could arrange the overall thing by shifting around the containers. And that would be 3 factorial. How do we get 4? The 4 comes from the fact that B and D within their little, how many ways are there to arrange B and D in their seats? 2, yeah. And then how many ways are there to arrange C and E in their seats? This would also be 2. There are 2 ways to arrange C and E in their seats. Oh, there's 2 ways to arrange them because they could be CE or they could be EC.
Yeah, they can just switch.
This is just
seats,
looking at the container and not the other things around them.
Yeah,
Actually, I think I just have an easier thing. Okay, so like, can we just forget about a container really quickly? Just forget about a container. Like, just take E and C, forget about them. Okay, pretend they never came to the movie theater, all right? At this point, we only have one container, and B and D are best friends, all right? They love each other and they want to sit next to each other, okay? So we only have 2 containers at this point. So B and D could sit at the most leftmost seat. So B and D could sit at the most leftmost seat together, like the 2 leftmost seats together. And then A could be at the right, or it could be vice versa, right? So there's actually 2 ways that could happen, right? So B and D at the left or B and D at the right. So only 2 ways that could happen. Now, if B and D switch seats, so I can't wait. Okay, well that's not what I wanted to do. So if B and D switch seats, that would give us a new combination, right? So that's 2 more that's like 1 more combination here. And then if we did it the other way, it would be another combination. So that switching of seats gives us twice as many permutations. That just gives us 4. So we're doing the same thing except with another container. So this time we're just doing it with another container. So 3 containers, 6 ways. Now, B and D could switch seats, which gives us twice as many permutations there. But E and C could also switch seats. So that's another twice as many permutations. So that gives us 24. Okay. What if they all sit in that one box, but they are side by side with that best friend, right? Okay, well you could think about that, but we don't have to make another box. These guys are all sitting side by side, right? So you guys are overthinking this. You guys are overthinking this box, right? This box is figurative. We're just pretending that there's an actual box, like so we can think about this problem in an easier way. We're just basically saying that if they want to be seated next to each other, then they can kind of be considered one rate, like one person in a way, but in this one container, so we can like arrange them in their according fashion.
The purpose of the boxes, like the boxes aren't like real. We're just using them
Yes,
to
they're
better
not real
understand the
boxes.
problem. The purpose of the boxes is just to keep like the people who are supposed to be sitting next to each other, like sitting next to each other. Because if we didn't
Yeah.
use the box, then C could basically sit wherever we want.
Yeah.
Then
exactly.
again, this is just because when we're calculating it, we want to consider these people together. That way we can keep them like sitting next to each other.
So it's basically a 3 factorial, and then times 2 times 2. It's like 3 factorial is the 3 containers, and then the times 2 is from each of the containers getting swapped around.
Yeah. Yeah, that's a good way
Okay.
to put it.
Yeah,
By the
okay.
way, for the
So-
question, is there any numerical way we could do it? I mean, the numerical way is to use this concept of boxes,
Yeah, it's 3 factorial times 2
swapping the
times-
boxes around and then swapping the items within those boxes.
So I think the thing that you guys are struggling with, I think it's like just the idea of boxes. Okay, so these boxes are completely figurative. They're just there so that these people sit next to each other. Because if the boxes weren't there, like Amy said, they could just sit wherever they want. But these boxes, like we're like implementing these boxes in our mind, right? So it's not really like they're not real boxes. We're just utilizing like this concept so that we could like visualize E and C sitting next to each other and like and that just helps the problem like, helps us solve the problem in an easier way. I think you guys are overthinking these boxes. So essentially, these boxes are just there so E and C and D and B sit next to each other. We don't care how they sit; they can switch, but as long as they're sitting next to each other, the boxes have fulfilled their purpose. So if we look at this in a broad way, there are 3 total containers. How many ways are there to arrange 3 total containers? 3 factorial equals 6, right? Well, the issue here is we're not considering the combinations within the boxes themselves. So if D and B switch, that's another times 2 ways. And if C and E switch, that's another times 2 ways. So you get 24.
I know you guys aren't completely sure how this works. However, we do need to move on a little bit
Yeah, we
because
need to
we've been
move
like
on.
spending a long
We
time.
spent a lot of time. We spent a very, very long time on
Oh,
this
by the way,
problem.
the times 2 is not for exactly when they switch. It's just that they could be sitting in the order BD or they could be sitting in the order DB.
Exactly. Yeah. So it's not. Yeah, it's not when they switch. Yes, it's like it's for each. Okay, I don't know how to properly explain it, but yeah, it
Yeah.
just depends. on
Different
the order.
arrangements.
Yeah. So if B were to the left, I think that's actually a better way of putting it. If B were to the
Okay.
left to the right, then that'd be completely different than B to the left and B to the right. So yeah, we can
All
move
right.
on anyway. We have to move on.
Yeah, we do have to move on. We're a little bit behind. Okay.
How many ways are there to arrange the letters in the word banana?
Yeah.
This is the thing that we were talking about. Advika, how did you get 60?
So in these there are repeated letters. So like in this, if we were to write banana, we could write that a lot more other ways just
Mhm.
by switching like the N's and the A's.
Mhm.
So first, we do 6 factorial, which is 720.
Mhm.
So that's what normally that's what the answer would be, but that's not the case here. So first I started with like the A's. So I divided this by 3 factorial,
right?
which is 6. So it's 720 divided by 6, which is 120. After that, I divided by 2 factorial because of the 8 ends. So after I did that, it's 120 divided by 2, which is equal.
Yeah, you did. That's exactly how you're supposed to do it. So for some people who don't understand, okay, so how do we not consider exactly? So look, if I have banana, right, I can move this a here and this a here. So if we just did 7 factorial, this same arrangement of banana would be considered twice, and we don't want that to happen, right? So what we do is we divide by the total number of repetitive letters. So how many repetitive letters are there in A? Well, we know there's 6 total ways to there's 6 total letters in banana, and there's 6 factorial total ways to arrange banana, right? But some of those ways are duplicates, right? So, and like we need to count how many individual letters are there, and we take that factorial. So if it was there's 3 A's here, right? So it would just be 3 factorial. There are 2 N's here, so then we do 2 factorial, and then we just simplify and we get the answer that I got, which is 16. Well, B
The
isn't being
reason,
repeated. And even if
yeah,
we were to put B, 1 factorial is just 1. So it wouldn't really matter. We don't really need to put B since it's not being repeated. And the way this works is because, there are multiple ways that banana could be arranged, but some of those ways would just be duplicates of one another. And basically, by counting this repetition, like, we kind of eliminate those extra ways. Why do we divide instead of subtract?
I mean, dividing is kind of subtracting. I mean, if you think about it, we could just do the same thing by subtracting 6 factorial. We could subtract all the overcounting ones. It's just by dividing, it's a little bit more efficient.
Yeah. So you guys might not understand how this works, and it's actually it's not that it's not like not very difficult how it works, but for the sake of time, we're not really high on time either. We'll probably just move on as long as everybody understands how we approach this problem. Because by counting the individual variations of each letter, and if we can like eliminate all the repetitive. So, Amy, if you could move on, you can see this problem, and then you guys can, when we learn formula for factorials, I just wanted to ask, we will learn that pretty soon.
Yeah, preferably very soon in
Very
this
soon,
lesson.
because we don't have too much time
Yeah.
either. So we spent a lot of time on the beater problem, but it's fine. It's fine as long as you guys at least try to have at least got a better understanding of how we could approach that. Yeah, you guys can solve via sticky notes. I can call someone to solve this problem. Oh yeah, actually it's okay. Yeah, all of you guys can solve it. That'd be better. Yeah, everybody have their own sticky note to solve this problem. Remember what I told you guys on how we approach.
We have one correct answer in the chat. So yeah, Sharvie, your answer is right.
That's good. Good job.
Okay, I don't know. I'm just gonna go ahead and explain it. Again, we're gonna use our strategy for the repeating letters.
Wait, Amy, do you
Yeah.
call someone instead because
Oh,
we have
okay.
a writing chat, and I'm just gonna call the person who did that. Let's see.
All right.
Sharvi, do you want to explain how you got your answer? Because you got the right answer.
Yeah, so what I did was there are like 8 letters in the name Jonathan, so I did 8 factorial, but the N and the A are repetitive and there are 2 N's and 2 A's, so I did 8 factorial divided by 2 factorial times 2 factorial.
Yes,
That's
that's exactly right.
And then what does anybody know what we get when we expand it? Well, it's fine. We don't need to solve that.
Yeah, the answer
Looks
is
like you guys are getting
10,080.
yeah, it looks like some of you guys are getting like
Okay.
some of you guys are getting something other than
Should we move on to
10,000.
combinations now?
Yeah, we
guys?
should move on.
All right. Hopefully we can get this done in. Oh, okay. The okay, I'll try to answer this question as quickly as possible without confusing anyone. So, since okay, we do 2 factorial times. We divide by 2 factorial twice because there's 2 repeated A's, so we have to divide by 2 factorial. But there's also 2 repeated N's, so we have to divide by 2 factorial again. The reason for dividing is because if we didn't divide, then if we interchange the N's, those 2 arrangements would be considered the same, even though they are, or sorry, those 2 arrangements would be considered different, even though they're technically actually the same because it's just the letter N, they're the same. So yeah, we have to divide by 2 factorial and 2 factorial because there's repeated letters, 2 A's and 2 N's.
Yeah.
Okay. Okay, now to combinations. So combinations are different from permutations. You would use combinations in a problem like this. Michael wants to pick a random combination of 3 letters from his name, where each letter can only be picked once, but he picks all the letters at the same time. For example, MIC is one combination. AEL, ICH, MIH, MEL, those would all be combinations. However, AEL, LEA, EAL, and ELA, those would all be considered the same combination because they're the same 3 letters, just in a different order. But the thing is, in combinations, the order doesn't matter. So, for example, if I pick 3 random highlighters from my desk, which is orange, yellow, and green, it doesn't matter what order they're in. Like, I'm switching them around right now. It doesn't matter what order they're in. I still have the 3 colors. This is what a combination is because the order in a combination does not matter. So unlike a permutation, in a permutation, I would have actually 6 different possible permutations of my colored Sharpies because I could put them in different orders. I could have like the orange first or the yellow first or the green first. But in a combination, that doesn't matter. It's just 3 colored Sharpies. So
Yeah, exactly. So in combinations, the order doesn't exactly matter, and you have to be able to identify when to use permutations and combinations.
Yeah,
So
and
we can
basically,
move on to it.
yeah, I'm just gonna give some quick examples of combinations. Picking things out of a jar, but you're pulling them all out at the same time. That could be a combination. Choosing something like, oh, like what sandwich, what, like, I don't know, what shirt do you, I mean, that would be, it depends. Okay, so a lot of times when you're choosing something, that would be a combination. So let's go over how to calculate combinations. In Michael's problem, we want to find the number of combinations of 3 letters from his name. Oops. Okay, we can first approach it just using our old permutation strategy. We have 3 blanks, and we basically have 7 choices for the first letter, 6 choices for the second letter, and 5 choices for our third letter. This is just using the fundamental counting principle. So this would be 7 times 6 times 5, which is 210. However, there's a problem. You see these 6 arrangements down here? This side, the left side, are all the permutations. However, all of these in a combination would be considered the same. It would just be the letters M, the letter I, letter C. Because if we use this with our permutation strategy, we're choosing the letters in a specific order, even though order doesn't matter in a combination. So because of that, we have to divide the number of permutations by 6 factorial, or sorry, not 6 factorial, 3 factorial, because for the 3 letters, there are 6 ways to arrange them, but since arrangements don't matter, we have to divide. Someone asked the difference between combinations and permutations. So I'm going to illustrate this again with my highlighters. For permutation, I would be arranging what order the highlighters are in. So this is green, orange, yellow, and then if I mix them up, I get green, yellow, orange, and then if I mix them again, we get yellow, green, and orange. That would be a permutation. However, if I just have a bunch of markers, I have a yellow one and an orange one and a green one. They're not in any particular order. I just have them. That would be a combination.
Here's another way to think about it. So if I have like 5 people, if there's a group of 5 people and I need to choose a president, a vice president, and a secretary, choosing 3 people there is where order would actually matter because there are different roles. They are different roles. So that would actually be an example of permutations. But if I were to just choose 3 of the same role, for example, that same group of 5 people, if I wanted to just choose 3 chairmen instead of, a vice president, president, secretary, this would be combinations because it doesn't really matter. It doesn't matter like the role because all the roles are the exact same. So that's where order doesn't matter. Like the order I choose the people in doesn't matter. So if in the first scenario, if I'm choosing a president, vice president, secretary, and let's just say I choose people A, B, and C, the group A, B, and C has different variations inside of the group itself, right? Because A could be president, B could be vice president, C could be secretary, or it could be B is president, C is vice president, A is secretary. But if those 3 same people were chairman instead, it wouldn't matter. So I wouldn't really have any variations of A, B, and C since they're all the same role. I couldn't really say A is this chairman, B is this chairman. No, they're all the same role. They're all the chairman. So it wouldn't matter. So that's a really good example for the difference between combinations and permutations.
Okay, so basically, back to Michael's problem, since we're trying to find the combinations, not the permutations, our previous permutation strategy has to have a modification to it. Previously, we got 7 times 6 times 5 as the number of arrangements. However, since the order doesn't matter, we have to divide by 3 factorial, which is in fact very similar to what we just did on the Jamboard. It's just I'm now putting this into perspective. This is a combination. So we would get 7 times 6 times 5 divided by 3 times 2 times 1, and this would give us 35. So there are 35 possible 3-letter combinations of Michael's name. And in case you want this into a more formalized strategy, Michael's name has 7 letters in it. We want to choose 3 letters. So there are 7 times 6 times 5 permutations of 3 letters. However, the number of combinations is 7 times 6 times 5 divided by 3 factorial. This is because for every combination of 3 letters, there are 6 permutations. So we have to divide by 3 factorial. And we can express this as 7 choose 3 because we have 7 objects, or in this case, it's letters, and we're selecting 3 of them. Are there any questions? Okay, where did I get 6 and 5 again? Okay, this is because Michael's name has 7 letters, and since we're choosing in a normal permutation, we would choose the letters. There would be 7 choices for the first letter, 6 choices for the second letter, and 5 choices for the third letter, because after we choose 1 letter, we can't use it again. So are there any questions? I know okay, I don't understand why you divide by 3 factorial to get the combination. Okay, I'm gonna go back to this picture. This down here, these are all like permutations of 3 letters, right? However, the problem is in a combination, the order of the letters doesn't matter. It would just be MIC in just MIC, but not in any particular order. And if you notice, there are actually 3 factorial permutations for each one combination. So in order to get it from the permutations to the combinations, we have to divide by 3 factorial. Because there are 3 factorial ways to arrange 3 letters. I hope that made sense. If it didn't, tell me. Okay, that's good. Yeah, so are there any other questions? No?
Then we
Okay.
can move on.
All right. Okay, here's the formula for combinations. I know someone was asking about that. We can, when we're talking about choosing, because in our example, it was basically 7 objects and we want to choose 3 of those objects. However, we can basically do this with any number. So we could do n objects, but we want to choose k objects out of that. So we can denote that with the letter C, where C is sort of like combinations. I don't know, combinations, choose. N choose k, which is basically the thing we just did, would be n factorial divided by k factorial times n minus k factorial. This is a formula for permutations, or sorry, combinations. However, I personally think this is a little bit confusing. I think it's better illustrated with some examples. So
Yeah.
for this, okay, I'm just gonna show a couple of examples. If you guys know the answer, you can just put it in the chat. So for the first example, we want to evaluate 5, choose 2. So this is basically like saying there is a guy with 5 letters in his name, and we want to choose 2 letters out of his name. So to do that, we would do 5 times 4 divided by 2 times 1. That equals 10.
Amy, can you put that inside the formula? Because I don't think they've
Or
learned
I
to
could
truncate
substitute in the
it
formula.
yet.
Okay.
Yeah. they
Now
haven't
the
learned how to truncate
yeah,
that.
I just think this way is more clear, but sure. Okay. If you were to just if you were to directly just plug it into the formula, because I took a shortcut there, you would get 5. Okay, I'm going to leave out the multiplication signs. I hope you don't mind. 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 divided by 2 times 1. Yeah, that's where the 3 went. Now, the reason where I got 5 times 4 divided by 2 times 1 is because if you notice, this part and this part are the same. So we can cancel this out.
Wait.
That's,
I have a
yeah.
question.
Yep.
It says 5, value of 5, choose 2, and k is supposed to be 2. Why'd you do 3, 2, 1 instead of 2?
Yeah, you're right. I did it backwards. Sorry. 2 times 1, 3, 2, 1. There. Okay. Same thing, but yeah, sorry. Yeah. You know, I actually sort of just derived it. You can derive it from the permutations thing. Basically, the number of, when you're going from permutations to combinations, for each combination, there's going to be, for each combination of k objects, there's going to be k factorial permutations of that. So that's why you have to divide by okay, it's a little bit confusing.
I don't think we should go over how we derive the formula.
All right.
Yeah.
If you want to, you can go to the previous slides after class and look at it, because you might get some hints from that.
We're allowed to look at the slides, right?
Yeah, we're gonna be sending it, and also, yeah, deriving the formula is actually helpful because when you derive formulas, you have a really good understanding of how something works. So you're always gonna be able to use it. There's no memory needed. But for the sake of this class, we're just gonna end the time as well. We should probably just move on.
Yeah.
So
5 choose 2 would be 5 times 4 divided by 2 times 1. So I'm just going to illustrate the rest of these, but I think because this is pretty important. For 4 choose 3, it would be 4 times 3 times 2 over 3 times 2 times 1. This is when I just jumped to the end. So if I use the formula directly, we have 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 1, which you can cancel those out, and this would be 4. And yes, the last one is 84. The last one, it would be 9 times 8 times 7 over 3 times 2 times 1, which is equals to 84.
So
Questions?
something that you'll notice here is that the way that Amy gets that shortcut is because you see the 3 at the end. That basically tells us that we only need to write down the first 3 products of the factorial. So if it was 9 times 4, it would instead be 9 choose 4, 9C4. It would instead be 9 times 8 times 7 times 6 divided by 4 factorial. So that's the way she gets that shortcut. And yeah, everybody should be using that, like, because it's just so fast. It's so
Yeah.
fast. Okay,
Okay, I'm gonna move on now.
we can move
All
on.
right. So we can now use this to solve combination problems. So let's look at a problem about choosing marbles. John has, oh, Sai, you can do this.
Yeah, okay, that's fine. But like John has 11 different colored marbles in a bag. How many different combinations of 2 marbles can he pull out of the bag? So remember that this is a combinations problem. So it doesn't matter what order we pull the marbles out of the bag, like what order the colors are in. So that doesn't matter at all. So yes, exactly. A lot of people in the chat already have the correct answer. It's just 11C2. And remember the shortcut that I showed you guys. So we only need to put 11 times 10 and then 2 factorial, which is just 2. So then we get 55. It's really, so this problem is quite straightforward. And it looks like a lot of you guys have understood how to do this, and it's pretty easy. So good job, you guys. Does anybody have any questions? Are there any questions? Like, just put anything. It can be about what? Wait, what is it? What is what? Can we do the rectangle problem? We're gonna do the rectangle.
Almost.
I
Well,
don't
we
know
can
if
do
we'll
that
have
at the end.
time
At the end.
for the-
Or
I don't know if
maybe
we'll have
like
time
if
for
you
the
guys
rectangle
want to
problem.
stick around to see us do it, then yeah.
Yeah, if you guys want to stick around, we'll do it at the end, like at the very end. So probably not during class time. Wait, what is it? Tanisha, what does that mean?
I think it's probably
What's
about
the-
the answer, maybe.
Yeah, it's
That's
55.
Okay.
Yeah, the answer is 55. Do you understand how I got 55?
Yes.
Okay, that's good. We can move on then, Amy.
Okay. All right, another problem, choosing classes. Walter needs to choose his classes for the next school year. He wants to choose 2 math classes, 2 science classes, and 1 history class. However, his school offers 4 different math classes, 3 different science classes, and 5 different history classes. How many combinations of different classes can Walter pick? Not schedule, pick. He's just
Amy, do
picking.
you want me to choose someone to try to solve this problem?
Sure.
Audit. Oh, Vishwa, you definitely. Well, you know what? I'll choose you for the next problem. So the ones, yeah, I know that I'm really happy that you guys are so enthusiastic about wanting to solve these problems, but I'm just gonna choose some that we haven't heard from this class. If that's, and then I'll choose you guys in a later problem. Audit, do you want to try to solve this problem? Hello, Audit. Okay, well that's fine. Okay, looks like we have a lot of people that want to solve problems. If there's enough problems, I'll try. Um, let's see who else have we not heard from. Deepika, do you want to try to solve this problem?
Yeah, I can solve this problem.
Okay.
So, I'm not fully sure if this is the correct method, but so I was gonna do 3 different combinations. So like for the math classes, 4 choose 2
Yeah.
plus 3 choose 2 for the science class,
Mm-hmm.
and then plus 5 choose 1 for the history class.
Yep. And
So
I mean,
for the math class, it's 4 choose 2. So it'd be 4 times 3 over 2, so it'd be 6.
yeah,
Then this science would be 3,
yeah,
and then history would be 5.
yep. Good so far. Now what do you
And
do
then
with these?
we would add these.
That's almost not add.
Multiply.
Yeah, multiply, because remember the fundamental counting principle. We have these different events. He's choosing the classes for different subjects. So we would actually have to multiply these.
And the answer would be 90.
Yep.
That's it.
Okay,
Yeah.
great job.
Pretty easy. Pretty good job. I mean, I would say a good job. Yeah, good job. Yeah. It's not a difficult problem once you get the hang of it. So yeah, these problems get much easier once you get the hang of combination. So good job. We will move on to the next problem, and let's see.
Tanisha, do you have a question?
Yeah. For this question, I am still confused on how you got 4 choose 2.
Okay.
Why not
Tanisha.
like 3?
All right. So since Walter needs to choose 2 math classes, right? And there are a total of 4 math classes he can choose from. So to find how many ways he can choose 2 math classes out of 4 math classes, we do 4 choose 2.
Oh, okay. Yeah. I
Yep.
did not see that part.
Okay, that's great. All right. Any other questions? Okay, we'll have another question. Okay, now we're going to look at arranging objects.
Like objects.
Okay. There are 5 oranges and 4 apples lined up on a table. How many arrangements of the oranges and apples are there?
I can call on someone, Amy, to try and solve this problem.
Okay, yeah, that'd be great.
Vishwa, do you want to try?
Okay. So first you do 5 factorial times 4 for the permutation. And then that would be over would it be 20?
Not quite. Think
Not
about it. How many
quite.
objects are there?
9.
Yeah.
9 objects. And think about it like a name. How do we do the name problem?
Oh, 9 factorial. Okay.
Yeah. I like that.
And then what do you do next? I mean, think about it like letters. You have like 5 of the same letter and 4 of the same letter. What do you do with those letters?
5 factorial times 4 factorial.
Exactly.
And yeah. So it would be 9 factorial divided by 4 factorial times 5 factorial, which, does anyone notice that this is actually equal to 9 choose 4?
Yeah, or 5. I was gonna say.
Or 9 choose 5. This is actually the same thing as 9 choose 5.
They're the same thing. Yeah, 9 choose 5 and 9 choose 4 are actually the exact same thing.
Yeah. So that would be equal to, if I'm not mistaken, 126.
Yeah, I also got 126.
Okay. So just to recap, for this question, you just treat the apples and oranges like letters. You do 9 factorial, and then you divide 4 factorial for the 4 identical apples, and then the 5 factorial for the 5 identical oranges. And from them, you just evaluate it. Yeah. I'm just going to quickly say that there is another way to do it. You could just consider the fact that the overall positions are determined by the 4 apples. So you could just do 9 choose 4 or 9 choose 5 for the oranges. Okay. Oh yeah.
And I think we're in a break period.
Yeah, we should take a break.
All right, everybody gets a 5-minute break. We're gonna see you back at 11:17. So have a good 5 minutes.
Tran, which problem are you looking at?
So you know what the homework we had after the first class, yesterday's class, we got homework, right?
Yeah.
And we were going over the solutions today.
Mhm.
My answer was close, but it was not correct because 0 is also a multiple of 2, right?
Yes.
But wouldn't that mean that 0 is also a multiple of 4?
Yeah, it is.
It
However-
should be 3 times 10 times 10 times 5.
Well,
Oh, wait,
0 can't be the first digit.
0 can't be the first.
Yeah.
Are we doing the Jamboard next?
Yes, I believe so.
Okay.
However, since we're a little bit short on time, we won't be doing every problem, and we may need to go a little bit faster. So, yeah.
Okay.
All right, everyone, we're just about done with our break period. So if everybody could join us back. We can get started. So maybe just go over the review.
It's gonna be a very quick review. All right, factorial symbol or operation, whatever. It denotes the product of all the whole numbers less than or equal to a number. And the distributive property is really, really useful when working with complicated factorial expressions. Okay, next, permutations are an ordered arrangement of objects. And you can use the fundamental counting principle to help you solve permutation problems. Finally, combination is an unordered selection of objects. So like you're selecting some items. And basically, I didn't write anything for that bullet, but basically they're basically derived from permutations, but you have to divide by the by the factorial of the number of repeated objects if you have repeated items. So we're going to the Jamboard. We're going to slide 12, right, Sai?
Yep.
All right.
Slide 12.
Okay, slide number 12. If you guys, if any of you all want to answer, you can just type in the chat and I'll probably pick someone. 6 representatives need to be chosen from school club. 3 of the representatives must be girls and 3 of them must be boys. If the club has 9 girls and 8 boys, how many combinations of representatives could the club choose?
I think some people asked to be called on Shreyan. Do you want to solve this problem?
Solve this problem. Okay, yeah, that's fine. Let me open.
Okay. If you guys are struggling to find the Jamboard, here it is.
So so we know that 3 of the representatives have to be girls, right?
Yep.
And only an order also does not matter too. So we're gonna have to do 9 choose 3.
Mhm.
And 9 choose 3 is equal to, wait, let me.
I think it's 84.
It's 84, yeah.
Yeah, I'm getting, yep, it's 84.
Okay, nice. Okay, so yep.
84. And then the amount of the boy representatives would be 8 choose 3. And that is 56, I think.
Yes.
Exactly, yeah. So then what do we do with those two numbers?
I think we have to multiply them.
Yes,
Yeah,
that's
we
correct.
do have they're different combinations. So we have to multiply these numbers instead of add them.
Yeah, so 84 times 56 is, okay, I'm gonna try and do that on paper.
And by the way, the reason why we multiply instead of add is because there could be a different combination of girls for each different combination of boys. And I know some of you guys get confused with that, so we can address that. Yeah, you can just do that on a calculator. So
Okay, yeah, I don't want to make a mistake, so I think it's 4704.
Yep, that's
yeah,
correct.
4,704. That's the right answer.
4,704.
That's the right answer. So wow, good job. You actually got that right. You did well. You did well. So good job on getting that right. And we're gonna move on to the next problem. Does anybody have any questions? Wait, does anybody have any questions though before we move on? Okay, no questions. Then I think Tanisha asked to also do a problem. Tanisha, would you like to do this problem? Tanisha. Tanisha. You there? All right. If Tanisha's not there, then I'm just gonna call someone else. Does anybody want to volunteer to do this problem?
Vishwa wants to.
Okay, Vishwa, you want to do this problem? Go for it.
Okay, so it says you can choose 1, 2, or 3 meat patties.
Mhm.
So that's 6 different possibilities for the meat.
Hold on.
How'd you
A
get
customer
6?
can choose 1, 2, or 3 meat patties.
But we're not arranging the meat patties in any order, right? So wouldn't it just be so?
Oh yeah, just 3. Okay.
Yeah, that's right.
And then any collection of condiments. So there's 8. So
Yep.
at most you could have 8 factorial.
Think about it.
Well,
Think about it.
that.
For each condiment, you can either have it or don't have it. So
What do you mean? It says any collection of condiments.
Yeah. The order
Yeah,
doesn't
but that, but
matter
that
for this.
order
It's just
doesn't
whether
matter.
we have it or don't have it.
Don't have it exactly.
We're
So
not like
the
putting
order
them
in which
into
those
a pile.
condiments, the order in which those condiments are laid does not matter. Think about it like that.
So just 8.
But another, well, it's not just there, right? Because we could either have a condiment or we couldn't have a condiment. So, for example, ketchup, I could have it or I couldn't have it. So there's 2 possibilities for ketchup, 2 possibilities for mustard, 2 possibilities for mayonnaise, and so on. So what would we do with that?
You would multiply them.
Yes, so we would get 2 to the power of
Oops.
8.
2 to 8
8.
times
So
3.
2 to the power of 8 times 3. So what would we get? I think we get 1,536 if I'm not wrong.
Oh, where? Okay, someone's
what do we
asking
get?
where are the 2 possibilities. So let me quickly explain. In this problem, it's actually a little bit different from some of the other combination problems we've seen because we don't actually use the choose, like a choose whatever thing. Instead, we're actually looking at how many possibilities are for each condiment. So for the ketchup condiment, you would think that there's only one possibility. You can just take ketchup. But the thing is, there's actually 2 possibilities for ketchup. You can either have it or don't have it. 2 possibilities, ketchup or no ketchup. And then you do the same thing for mustard. There are 2 possibilities. You can either have it or don't have it. And basically you do that for each of these. And then of course for the meat patties.
Total for the condiments. Yeah.
Okay, someone's confused and someone's understanding.
There are actually 256 ways, Amy. I don't think it's 2048. I don't think that's the answer.
Times 3.
I got 768.
Yeah, I also get 768 because 2 to the power of 8 is 256.
2 to the power of 8 is 256.
But you have to multiply by 3.
Yeah, 256 times 3 is 768.
Oh, shoot, you're right. Sorry.
That's fine. All right, so we do get 768. I think we have time for actually.
Wait, let me quickly just run through it one more time. Okay. For each condiment you have, for example, ketchup, we can either choose to take it or like don't have it on our hamburger, right? So for each of these, ketchup, mustard, mayonnaise, tomato, lettuce, pickles, and cheese and onions, for each of those, there are actually 2 possibilities. We can take it or we can choose not to take it. So for each of them, since there's 2 possibilities, it'd be 2 times 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 2, 2 to the 8th power. And then we, of course, we have the patties. Since a customer can choose 1, 2, or 3 patties, there are 3 choices for that. Yeah, yay. Okay, so then we, of course, just multiply them together to get the answer.
All right, I think we can do one more.
Okay, one more. Oh, I like this question. If 10 straight lines are drawn on a piece of paper, what is the maximum number of intersections that there could be? And by the way, what I mean by like straight lines is like a straight line. There's no like curvy thingies. Don't be like drawing like circles or something, and don't let the lines intersect each other, or sorry, intersect itself. It's just they can intersect each other like this, just not anything wonky. Normal lines. 10 straight lines on a piece of paper. What is the maximum number of intersections there could be? Don't 11? Draw it out. No, not 11.
12?
I see some people are thinking, would it be 2 to the 10th? No, but you're thinking, I think you're starting to get on the right track. Think about it. If you, someone asked, would it be 10 choose 2? Why were you thinking 10 choose 2? Or were you just randomly trying to figure out, oh, because 2 lines are used to intersect. Yeah, that's true. 2 lines are used to intersect. There are 10 lines. Also, how would you know 10 choose 2 is the maximum number? Well, let's just say this. Sharvie, you're right. It is actually 10 choose 2. And the reason being because if you think about it, let's just draw like one line first. So, and then let's draw, so the maximum number of intersections possible would only be if every line intersects all the other lines, right? So that means that we would need to take every single possible combination of two lines and make them intersect. However, we don't need to figure out how to make them intersect. We just want to find the maximum number of intersections. So we can just assume they're all already intersecting each other at the maximum. And we just need to count how many intersections there are. And that would be 10 choose 2 because we have 10 lines, right? And we're just choosing 2 of them and counting because wherever there's 2 lines, we should have an intersection somewhere. So the answer would just be 10 choose 2. I hope that makes sense to you guys. And just saying this can work with any number. If you have like 100 lines, what would you do?
A 100 choose 2?
Exactly. We would just do
Okay,
100
and
choose 2.
for those of you that don't understand exactly how this works, think about it like this, okay? So if we choose any 2 lines, right, those 2 lines have to be intersecting, right? Because if we have the maximum number of intersections, any 2 lines have to be intersecting, right? So 10 choose 2 basically gives us the total like combinations like of 2 lines that we can have, and each of those combinations has one intersection, right? Two lines can't intersect in more than one point. Like I think everybody knows that, right? 2 lines cannot intersect at more than one point unless they are the same line, especially since they're straight lines as well.
But if they're the same line, we don't count it as 2 lines.
Yeah, obviously, yeah, of course. But yeah, so 2 lines cannot intersect at more than one point. So if there are 10 lines, when we choose 2 of them, any 2 that we choose are intersecting at least, not at least, are intersecting at one point. Okay, so that 10 choose 2 gives us the total number of combinations of intersecting lines and thus gives us the total number of combinations. Does everybody understand? By the way, the answer is 45. So
yeah.
I don't understand.
Yeah. Okay. Everybody understands, right? That's nice.
No, I actually don't understand.
Okay. So if you think about it, in order for the lines, we have to first ask under what conditions will there be the maximum number of intersections? And the only way that can happen is if every line intersects all the other lines, right? Because there can't be, the lines can't intersect any more lines than there are on the paper, right? So let me just say that again. The maximum number of intersections occurs when every line intersects at all the other lines. That means that no matter which 2 lines let's just say you pick 2 random lines. It doesn't matter which 2 lines you pick. Whatever lines you pick, they should have an intersection somewhere. So then that means that the number of intersections will be the number of lines choose 2 because it takes 2 lines to make an intersection. I hope that makes sense. So
yeah. Well, we have to explain the homework right now.
Yeah,
so
we can explain the homework.
we're just gonna go to the homework real quick.
Yeah, if you guys really need to leave, you can, but we hope you can stay for the homework explanation. Okay, I really like this strategy. I know this was originally.
Amy,
what?
go over the homework in the actual slides as well.
Oh, in the actual slide. Oh, the slides thing. Oh, okay. Sorry.
Yeah.
Oh, shoot.
And then you forgot to showcase your amazing questions.
Okay, homework, as usual, 5 questions. The document is here. Yeah.
All right, move on to your question slide. That's pretty critical.
Oh yeah, question slide.
Yes, Amy worked really hard on this one as well, guys.
Yeah. Oh, looks like you guys are trying to figure out how many rectangles there are. Well, I'm gonna tell you all
Alright,
the
we're gonna go
answer.
back to that. Okay, let's go back to the
All right.
rectangles.
Okay, this is like the great. I really like
Just
this
so you know,
spreadsheet.
just so you guys know, this isn't official class time anymore. Anybody's free to leave. We're not even really in class anymore. So
Yeah.
class is like, if you want to stay behind just to see this, then you can, but you don't have to. Just
Okay, so I know you guys already know what combinations are, so we're going to use that to solve this rectangle problem. So basically, casework would take a long time to solve this problem. So instead, let's just look at let's dissect a rectangle quickly. We have a rectangle, right? How many vertical sides does a rectangle have?
2.
Vertical sides. 2. Yes, there are 2 vertical sides. And how many horizontal sides does a rectangle have?
2.
Yep, 2. Okay, now let's go back to our little diagram. Any rectangle in this diagram is going to be made up of 2 vertical sides and 2 horizontal sides. Or you could think of them as 2 horizontal, 2 vertical lines. So let's first look at how many possible side lengths this rectangle could have for like its vertical sides. So I'm gonna put a blue line over each of the little vertical grid lines on this grid. So in order to make a rectangle, we need to choose 2 of these grid lines. How many ways are there to do that? There are 6 vertical grid lines, and we need to choose 2 of them to make up 2 of the sides of the rectangle. So how many ways?
2?
Yeah, it would be 6 choose 2. So I'm just going to write that down up here. 6.
That'd be 15.
Yes, 15. All right. And now let's look at the horizontal sides. There are 1, There are 1, 2, 3, 4 horizontal grid lines. So we need to choose 2 of these to make a rectangle because a rectangle has 2 horizontal sides. So how many ways are there to choose 2 of these to make the size of a rectangle?
4 choose 2 or 6?
Yes, 4 choose 2 or 6. So now what do we do with this?
Multiply to get 90.
Yes, exactly.
Yep,
15 times 6 is 90. There are 90 possible rectangles. So I hope you guys can see how you can use combinations and some clever logic to try to count the number of rectangles in an image. Because for this image, casework is just such a pain. So yeah, and if you really need some convincing to really like accept the fact that you could just choose 2 random sides and two random vertical lines and 2 random horizontal lines, and it'll make a rectangle. You can just draw on it, choose 2 random sides. Boom, there's a rectangle right here. So, yeah.
Where do you get 6 from? Like 6 choose 2?
Yeah, that's because there's 6 vertical lines. 1, 2, 3, 4, 5, 6.
Oh, okay.
Mm-hmm. So are there any questions?
Yeah, this problem is pretty great.
So I just wanted to say something in the classroom. I think somebody didn't get to join today.
Oh, someone didn't get to join.
Yeah,
Oh.
she was asking to let her in the meeting.
Okay.
What happened?
Oh, yikes. I mean, okay. I don't know what happened.
I'm on my mom's account, so I'm already in.
Oh, okay.
Ah.
Okay, that's great. Yeah, I was just admitting whoever I saw, so okay. So yeah, if you guys don't have anything else, I mean,
you guys are, yeah.